Dimi Racordon about borrow checking Hylo.
Thank you very much. Why I cannot see my presenter notes? This is not good. All right, technology is great. Hello everyone, I'm Dimi. I'm a postdoc at EPFL, but I did most of this work during my stay at Northeastern University. So that's why I mentioned the two institutions. And today I'd like to talk about a programming language I'm developing with amazing people. One of these people is my co-author, Dave Abrams, who happens to be the person behind the Swift standard library. So if you've done any Swift language, you might see some resemblance. It doesn't come from nowhere. So what is Hylo? Hylo is a programming language for high-level systems programming. Think about device driver, 3D rendering engines, or even compilers, right? It is designed to be safe by default, fast by definition, and it has a strong bias toward generic programming. Today, I want only to focus on the two first goals. The generic programming is a whole thing on itself, but yeah, I think with safety and efficiency, our plate is already full. So what do I mean by safety? I think it deserves some definition because safety is a kind of overloaded term in the PL community. So by safety, I mean freedom from undefined behavior. And this is a nice and concise definition, but if you're not from a C or C++ community, maybe it's not that helpful. So let's dig a little deeper with a C++ program. I know C++ is very scary, but don't worry, it's the only example we'll have today. So the first line here is creating a vector. This is a dynamic array, and it's initialized with the French and Japanese translation of hello. And then the next line is getting an iterator on this vector. This is also like a scary term in the C++ community, but just think as kind of a pointer to a part of the vector. And then we call resize. And this method says, I want the vector to have enough storage to contain at least here 10 elements before you need to reallocate storage. But keep everything that you had already. And then we want to dereference the iterator we had to show what's the first element. And now, boom, this program has undefined behavior. The problem is that when we call resize, we might have reallocated new storage, and so it invalidated all pointers we previously had on the vector. So when we try to dereference here the iterator we had, we cause undefined behavior. So this looks like a plain old bug. So how bad is it exactly? We know bugs, right? Well, it's really bad because undefined behavior means that this program can do literally anything, including summoning demons from your nodes. But more seriously, what this program can do is start interpreting data in your program, arbitrary data as code. And so you can open all sorts of security issues with that. So what can we do about these kind of bugs? Well, if you're using a language like C++, basically the only choice you have is to be very careful. But if you're using a safe language like Scala, for instance, we had a very nice presentation about Scala before, then you don't need even to care about that because undefined behavior cannot happen. It's a safe language, and by definition, safe language don't have undefined behavior. So for instance, this is a Java program. It's not as nice as Scala, but still makes my point. This program is a transliteration of the C++ program we had before, and it also has the same bug. But there is a difference. When we execute the last statement here, we have invariably an exception thrown at runtime. And this is much, much, much better, because at least now we kind of reduce the realm of possibilities there is when we write a bug. So we don't need to be so cautious anymore, because at the very least, we have a safety net. And this safety net is very important because, well, even amazing developers make mistakes sometimes. But if safe languages are that great, and they are, well, why C++ is still around, right? Well, the answer is efficiency, and this is the second stated goal of Hylo. When we write a program in C++, it gets compiled directly to machine code. And that's really nice because that means we can very closely describe the operations that we want to apply with great efficiency. That's because we are very close to the real hardware systems that runs our program. And the real hardware system doesn't care about lambdas, right? The real hardware system is just a dumb machine that does mutation on its registers or on its memory. So if with C++, we can write super complicated abstractions, very nice abstractions that we humans like, but we can get the guarantee that they are, they are compiled without loss of efficiency. And that's very important to us. This is in contrast with a language like Java that introduces a middleman in this whole process. When we write a program in Java, it doesn't get compiled to machine code. Instead, we get an intermediate representation that is executed by a virtual machine. And this virtual machine is on top of the actual hardware. So the advantage is that we can rely on this virtual machine to do all sorts of things, like dealing with memory for ourselves. Or it can also make a lot of checks and guarantee safety. So it's very nice, but it also comes at a cost. The first cost is that the middleman introduces a lot of delay, because the middleman is allowed to stop the world at any time to do some sort of operations that it feels it's appropriate. For instance, it may stop the world to reclaim memory. That's the cost of automatic memory collection. And okay, Martin told us that garbage collection is not a problem in practice. Well, I think it is for very specific applications, but even if it's not a problem, you still have other costs that come with the middleman. So for instance, it may also stop the world to try to come up with a more efficient way to run your code. That's just-in-time compilation. And it's often necessary because running bytecode on itself, as it is order of magnitude slower than running native code. So a JIT compiler can get you closer to what you have done when you, if you had written your code directly in C or C++. But you don't want this cost also, because there is warm-up and all sorts of things, right? And lastly, there is also the problem that the middleman imposes some tax on the abstractions that you want to use. So now when you define abstractions, it's no longer free. For instance, if we define here this vec2, it's kind of a pair here, the allocation of this object in memory uses a lot of boxed objects all over the place, and now if we want to access the elements of these vectors, we have to pay for pointer and directions. And cache locality matters, so this is also costly. Now, to be fair, compilers and JIT compilers, and we have a lot of smart people here working on these dynamic languages. They come up with all sorts of tricks to alleviate these costs using ahead of time compilation or just-in-time compilation of any kind of other code transformations, but none of these code transformations are guaranteed. There are optimizations that, when we are lucky, we have them. So if we want true guarantees about efficiency, we can't use them. The last thing I said I will just briefly mention is generic programming. And one thing I want to make clear is when I talk about generic programming, I just don't mean type polymorphism, right? When I talk about generic programming, I'm borrowing my definition from Alexander Stepanov to mean that it's the practice of writing algorithms in terms of the algebraic properties of the data on which they operate, without loss of efficiency. So again, this kind of efficiency comes up here. And so here, I won't get into too much details, but having a difference in the way your data behaves makes this practice a bit harder. All right, so let's address the elephant in the room. I've talked about high-level systems programming. I've talked about efficiency, zero-cost abstraction. I'm sure you're all thinking about Rust, right? And I'm also sure that the entire audience here is kind of familiar with Rust, but just to be sure, let's introduce the language a little. So Rust is a relatively young language that promises safety without loss of efficiency, because unlike Java, it doesn't rely on a virtual machine. Instead, it guarantees safety with kind of a sophisticated type system. So here we're looking at a very simple algorithm. It's not a useful algorithm, it's n squared, but it's just here to illustrate some concepts. This is a function that removes from one vector the elements of another vector. And it's surprisingly difficult to write this function in C++ safely. The problem is that we are using two references for efficiency, and when they alias each other, well, things can go very wrong, like the first example that we saw. But in Rust, because of the nice system of Rust, we don't need to worry that much, because Rust will guarantee that they cannot alias each other, because the first one is mutable, and so if there is a mutable reference, it cannot alias another reference in scope. So we have the guarantee that the safety issue that we would have in C++ cannot happen. In fact, if we try to force the issue, we will get a compile time error. The compiler will say, well, you can't do that because you cannot borrow s as immutable while it is being borrowed mutably somewhere else. But so Rust has very nice error messages. This is great. So it seems like it's a very good approach to a very hard problem, but it comes with cost, right? No free lunch and all of that. Rust is complex to use. It has a steep learning curve, and it's to the point that fighting the borrow checker is kind of a meme in the Rust community. The borrow checker being the part of the language that guarantees all of this stuff, right? So the first issue I would say is that first, these notions of references add a lot of noise to the code. If we were looking at this written in Scala, for instance, we wouldn't have to care about these sigils here, the ampersand, the stars, and everything, right? This is all additional costs, like cognitive costs we have to keep around. This is because we are dealing with references, but I claim that usually when we write programs, we don't care about what is a reference or what is a value. We just care about the value. We care about the real deal. We care about what the vector is and what the vector contains. We don't care about whether or not these things are references. The references are mostly there for efficiency. And if you look at how people write C++, for instance, it's very clear. Const reference means pass by value, but efficiently because I don't want to pay for a copy. Very, very clearly. So this is the first issue. And the second issue is that here it doesn't show, but to perform its magic, Rust uses lifetime annotations. And this is kind of a crazy example. Here we have 3 lifetime annotations, right? It's kind of a crazy object. So the first one, buff, is defining the lifetime of some buffer. And the colons say that it must be longer than decoded, which is the other one that represents the lifetime of decoded objects that are projected out of these things. And then we have yet another one that's labeling the decoding objects. Right? It's kind of a crazy example. To be fair, most code doesn't look like that, and lifetime inference is pretty efficient in Rust. We didn't have any on the subtract function earlier, but still, there is some code that needs to rely on this, and this is hard. This is hard to deal with. So even with all the niceties of Rust, the nice error messages and the aliasions and all of this stuff, I have yet to meet a Rust developer that doesn't long along when I say Rust lifetimes are a real struggle. And everyone agrees. Okay, so what can we do better? Well, here enters Hylo. I'm shamelessly plugging my language. Hylo does also the safety thing, but instead of using references, it uses something called mutable value semantics, or MVS for short. And the basic idea of value semantics is that it's ban sharing, it bans mutable sharing mutable state, but not mutation. So you can still do your mutation, your in-place mutation, as in any programming languages, but you cannot share these mutations with aliases. So here, for instance, in this program, we are mutating in place the first part of a pair. And this is like what we would write in C++. That is in contrast with language with reference semantics, in which if you want to guarantee like the independence of values, basically the only thing you can do is functional update. So for instance, in Scala here, we would have to reassign the pair to a brand new pair, and then we use S2 for the remainder of the program. So that works, but first it's kind of it adds some overhead, and it doesn't scale very well for deep data structure. And also now it's pushing a lot of pressure on the optimizer to recover the efficiency we lost with this thing. Because now we allocated a brand new pair just to, well, change the pair we already had. So all of these new objects in memory, we don't want them. And so in Hylo, we can do the in-place thing. So another important feature of the language is that it has a linear type system, meaning that all values must be used exactly once. So linear type systems are great for modeling resources, like memory, for instance, but they are notoriously difficult to use. Here, for instance, this program is actually wrong. If we try to compile it, it will say, the compiler will complain that S was consumed. It was already being used, because when we said var t equal S, we moved S to T. Okay, so this model is great. We can forget about all the issues with references and everything, because basically all values are unique, but it's hard to use. So Hylo has a few tricks up its sleeves to help with this issue. The first is to relax the definition of using. So most of the time when we use a value, we just want to read its content. We don't want to take its ownership and destroy it, right? We just want to see how it looks like. So in Hylo, we can say that instead of taking the value. We just want to pick at it. And so this is a let here instead of a var. A let is kind of an immutable binding to some value, right? And now it's only using to read, and so there is a distinction between using to read and using to consume. So the let binding is just reading S, and so now this program is fine. But what about consumption? Because I said it's a linear type system and nothing consumes either S or T actually. So am I lying? Well, the thing is that deinitialization is a kind of consumption, and it's usually inserted by the compiler itself. So the compiler can figure out you don't need S anymore, we can deinitialize it, and now S behaves like a linear value again. And this is important because that means we can attach behavior to deinitialization. It doesn't have to be just dumb deinitialization. We could do RAII. If you've done some C++, for instance, it's used extensively, we can do cleanup and all of this stuff. So what's nice about this is, well, you don't have a garbage collector, but do you need it though? Because it's infamous in C++ that you need to manage memory manually. But with this thing, we don't have any new delete or anything, right? It looks like what we could write in Scala. So we get the niceties of garbage collection kind of for free. Of course, no free lunch, and we will see some of the limitations later. So at this point, you might think that T is just as good as a reference, and I said there is no reference in the language, so what am I talking about? Well, it is under the hood, but what's important is that at the language level, at the user level, we don't need to think of these things as being references. They are just values. For all intents and purposes, T is an independent value and I can do anything I would do with a value. And the language will guarantee that this is true. And so if I try to trick the system and do an operation that would violate my assumption, the compiler will catch me. So for instance, here, if I try to modify S while T is extant, then this is a violation of my guarantee, because the guarantee would be T is an independent value. Its value cannot change if I don't mention T in any operation. And now here I've changed T, so this is obviously an error. So here I need to change my program, or maybe do a copy, or I'll rewrite my program in some way. But the hypothesis is that this kind of situation doesn't happen that often, because most of the time we just use values for reading. We can create write accesses too. So here it's an in-out access, the same as the let access we had before, but we are allowed to modify T. And again, T is an independent value for all intents and purposes, and also I'm able to modify it, and so I can write this program. If I try to violate the constraints, again, the compiler catches me and says, well, you can't do that. If you try to print S while T is being mutated, then the independence guarantee of S is violated, so please don't do that. And we can use these passing conventions on functions, and so this would represent, for instance, mutation across function boundaries. So this is actually the only way to do mutation across function boundaries, because we don't have references. So now we are ready to look at subtract again, and we don't have the pesky stars anymore. These things are just values. It's a bit nicer to read, I would claim. Okay, so we can write mutation across function boundaries, but what about accessing the values of a container? This is some Rust code here, and in Rust there is this getMut function. This is a very useful function that gets you a reference to the contents of a map, for instance. You have a hash map and you want to access the value for a specific key. And this is very useful to have this operation, because let's say you want to just update the value for a specific key, you don't want to pay for 2 hash lookups. And if you were using a pure functional programming language, you would even have to rebuild an entire map, which is crazy expensive, right? So it's very nice to be able to do these things in place. If you don't have references, well, it's a bit hard. So the thing we do with Hylo is that we say, well, instead of projecting the reference out, let me just execute the code that you want to do with your reference, right? And so now I keep ownership of all my parts, and I execute the code that you want, and then no one is the wiser. And this is captured by this inversion of control mechanism. So now the only thing we have to do is come up with a nice syntax, because users typically don't want to deal with higher functions all over the place, right? Except if you're a Haskell fan, I guess. So the trick, we took it from Swift. It's a subscript, and now at the call site it looks kind of traditional programming, right? You get a subscript of your map, and then you can do whatever you want with it. But this mechanism is actually even more expressive than the reference one, because we can project anything we want, even values that don't have an actual representation in memory. So for instance, we could say that, let's consider this UI32 is a collection of bits. It's a bit field. And the only thing I need to do is define a subscript that projects booleans. And so now I can yield the value of the boolean, and yield is kind of reminiscent to coroutine because it's exactly that. It's the version of control. The only difference in the subscript is that the subscript has exactly one yield on every code pass. It doesn't yield twice, it doesn't yield 0 times, it yields exactly once. And we can bundle different variants of this subscript. For instance, we can have mutable one, and now we can project a bool out and then get the value back in. And after the yield statement, we have a chance to apply the mutation back to our actual internal representation. So now I can really consider my UI32 to be a collection. And at the call site, again, it looks like traditional programming. So, okay, enough about the language. We're here to talk about compilers and implementations of these aliasing tracking things. So let's talk about the compiler. It has very traditional compilation pipeline, nothing very interesting here. What we want to talk about today is the IR generation phase, and this is where the borrow checking of Hylo happens. You might notice that it's not part of type checking. So you might quote me when I say type checking, I don't mean anything to do with the lifetime guarantees or the access of everything. Type checking is just figure out what is an int, what is a string. Then our generation is all about guaranteeing the access rules are satisfied. Okay, so our generation is decomposed in several steps. I don't have a lot of time, so I'll zoom a bit through it. But the first is IR lowering, which is translating this Hylo representation into an IR form. And this IR looks kind of like LLVM, so not getting too much into the detail, it's kind of this assembly thing, right? It's not very pretty to look at, but it has nice properties. Basically, it's SSA form, and it's convenient to do analysis and optimizations. We're mostly interested in analysis here. So we have registers, and registers corresponds to the variables of SSA. They are not directly correlated to variables in the language itself. So for instance, %1 is the allocation of the literal that we pass to the subscript, but they might be, this is the case for %8. And we do a lot of stack allocations. It's okay because these allocations will be optimized away by LLVM later on. And this stack allocation can represent the object lifetime of something, right? It's a memory cell, it's not initialized, and then you can put a value in it, initialized, and then you can put the value out. So it's easy to track. The initialization is inserted, as I said before. Let's go a bit quickly over these things. And now, what's interesting about this IR is that we have these access operations, which are ghost instructions. They don't have any meaning in the operational semantics, but they can be used by the borrow checker to figure out what's going on with the access. So here we're saying I want a set access on the value, and the set access requires the object to be uninitialized, and so here this is guaranteed by the compiler. Okay, I move a little. Access verification is not the most interesting. Last use analysis is just, we have non-lexical lifetimes like Rust. This is very simple algorithm. We figure out what is the last use of all of these things, and we insert end accesses for everything after the last use. Nothing very interesting. What I want to talk about, a bit over time, I'm very sorry about this, is definite initialization. So definite initialization is a popular static analysis technique, guarantees that every object is initialized before use. We extend this definition in Hylo to say is also uninitialized before being deallocated or uninitialized before a set access. And we do that with an abstract interpreter. So the only thing we do is to execute this program in the compiler in an abstract domain that only cares about the initialization state of the object. So we start here, we alloc some stack, and then we track what is the value in memory, and we move as we go. I think you get the idea. And if something goes wrong, we can either try to fix the program by inserting new IR, so this is how the initialization is inserted, or we can report an error. And exclusivity checking is the same thing. It's doing the ownership analysis, if you will. It's guaranteeing that you cannot have two in-out accesses. If we would try to run this program, for instance, we would figure out that it is an error because the state in memory would be something like that. And once we're done with all of these steps, we're ready to co-generate this thing. This is LLVM stuff. We don't have to care about this. LLVM is very good at optimizing this kind of stack heavy code. And okay, that's all I wrote for today. Sorry for going over time. Thank you for your attention. If you have time for questions, I'm ready to take one.
Okay, so we have a time for a few questions. Does anyone want to?
So your definition of safe is a bit loose in the sense that what is your compiler actually guaranteeing? Because just undefined behavior, if you don't catch an exception, doesn't prevent the program to crash, right?
Yep.
So what exactly is the compiler guaranteeing?
The guarantee is just no undefined behavior. You may crash, and you may try to access an array out of bounds. What you know is that you will crash. You will not run into undefined behavior.
Any other questions? Hi. I was thinking about this mutable value semantics, and it seems like sort of everything is a value unless you try to observe something that would reveal that it's actually a reference, and then you disallow that. Like, it's a bit philosophical, but isn't it a reference? Then you're just disallowing the things that would make it show to you that it is actually a reference.
Yeah, in a sense, yes. The difference is that the references don't show up in the type system. They're not a user level concept. You cannot store a reference to something. You can only store the value of something. And so, sure, you can think of them as references if you want, but it's as good as just to think there are accesses to values and accesses on which I have certain rights and duties. Because if they were like fully first-class references, then we would enter Rust territory and we would need to track lifetimes and all of these things.
Okay, thanks.
One more question, maybe?
Oh, yeah.
So about the limitations, can you write cyclic data structures?
That's the thing, right? So what about doubly linked lists? So yes, you can. There are a few tricks you can do. Basically, it's the same story as for Rust. You can do reference counting cells, so RC cells, and a lot of people write that in Rust. I think it's not the best approach. The best approach is just to rethink your programs. You can write arbitrary graph structures with adjacency lists. And it might sound foreign, say, oh yeah, it's a step backward, I want my references, but actually, you can write very nice and concise definitions of like graph algorithms using these data structures. So I think it's actually a win if you think more in terms of what is the values that I have. But yeah, this is the obvious limitation.
Okay.
Thank you very
I
much.
think that's all, so we can thank Dimi again.